And Professor Zabras is traveling, so he asked me if I would introduce our next speaker. My name is Karol Matouš. For those of you who don't know me, I'm a professor at AME department, and I also do a lot of computational science and engineering and large power computing, and lead our Predictive Science Academic Alliance Center. So today we have one of our own, Professor Alexander Dowling from Chemical and Biomedical Engineering Department. Alex got his PhD at Carnegie Mellon. We have been just talking about how beautiful Pittsburgh is. He is from around the woods, Michigan native, and went to University of Michigan for his undergraduate degree, if I'm not mistaken. And he joined very recently University of Notre Dame, and I will let Alex introduce his talk.
Okay, so thank you for coming. So I'm a chemical engineer by training, but I'm really perhaps a little more interested in applied math. And I just trick people in chemical engineering. So I'm interested in mathematical optimization and how it applies to energy problems. So kind of the grand vision is you want to be able to think about if you have a new material, right? And it has some given properties. Well, how do you optimize that material, and how do these properties cascade into like an optimal design, like a battery module? How does that cascade into like an optimal battery system, and how does that cascade into like optimal operation of the electric grid? So we eventually want to be able to do forward problems and then reverse problems in the sense of what would an optimal infrastructure look like starting from scratch, then how can we set systems, device, and material properties. So my main workhorse is mathematical optimization. So problems that are in this form or similar forms where we have some type of analytic function that we want to minimize. Could have continuous decisions, it could have discrete decisions. Like to express things in terms of inequality and equality constraints. We prefer to be able to express these either algebraic systems or differential algebraic systems. I'm particularly interested in very large nonlinear, non-convex problems that arise from a lot of chemical engineering applications. Thermodynamics is not nice, it is rarely linear. Also, I'm going to talk about stochastic, mixed integer, and I'm not going to discuss multi-objective, but I've worked on that in the past. So my past area of expertise, I've worked on CO2 sequestration, worked on solar, worked a little bit on electricity distribution, and getting it now into desalination, cogeneration, and a couple other technologies on this slide. Okay, so I think this will be kind of a tour of optimization methods that work with, and I'm going to frame this in the context of looking at electricity markets and how this impacts different energy storage technologies. So we'll look at multi-scale modeling and optimization, then discuss dynamic mixed integer optimization, so what happens if there's discrete decisions. Then give some background on stochastic optimization motivated by a cool little controls problem, and then finally give an outlook on some things I'm looking forward to doing here at Notre Dame, some collaborations that we're starting, and finding ways to interface with everyone in this room that's involved at the center. Okay. So for some background, all right. Perhaps you've heard of this idea of baseload and peaking power plants, right? A nuclear power plant, you can't ramp up and down. There's these peaking natural gas power plants. This paradigm is changing. There's a lot of new exciting technologies coming online, talking about large-scale solar with thermal storage, batteries, very important, and we even have smart manufacturing. So there are some chemical systems, actually examples in the world where people change their energy demands, their production schedules to accommodate large fluctuations in energy prices, and buildings too. So there are examples in literature where if you optimize the operation of the heating and cooling system, you can cut your energy bill by 30%, which is a lot of money. Okay. So the key question then becomes, if you have all of this data from the electric grid, or I should say, so these technologies in the grid, they're all coordinated by these electricity markets. We transact energy, so buying and selling megawatt hours, and ancillary services, and I'll get into this in a little bit. So the key question is, if you have all this historic data from energy markets, which is all publicly available, and you have a physical model for a technology, how can you rapidly predict the revenue opportunities for said technology from market data? How should you bid some of these technologies into multiple markets at a time? And how does this impact how we design technologies? So how good does a battery need to be? Or if we had a battery breakthrough, what would that, how would that cascade into the economics? Okay. So this is a very data-rich problem. So here's a kind of system of a picture of the California market. So each dot is an individual node where there are unique prices that vary in time. And California is complicated, so they have a day-ahead market where you're scheduling most of the demand. So they have a forecast for how much demand they'll need in an hour time resolution the day before. All of these dots are generators or aggregated together to be a virtual generator. They all bid into the market, and they get scheduled in this day-ahead market. And then there's a real-time market that makes up for the fact that there's always error in the forecast, right? But about 99% of the energy is scheduled in the day-ahead market, 95 to 99. So we can look at, and all this data is publicly available. It's painful to get at, but it's all publicly available. So looking at one node, we can make a histogram for 1 year. And we see, in the day-ahead market, this is fairly symmetric. But at these fast time scales, you get a lot of negative prices showing up and a lot of positive prices. This distribution becomes skewed. And we can also see this in time series. So the blue line is the day-ahead. That's pretty steady. There's a periodic pattern. There's a lot of noise in the real-time market. And this corresponds to spikes in the evening, which I'll get back to. It has to do with all the solar in California. All right. Can do frequency analysis of the dominant components by doing a Fourier analysis. And what we see from this is a little surprising. So you probably hear a lot about seasonal trends. Those don't actually matter. 97% of this variation is actually day-to-day or faster. So those are the types of time scales that you need to think about for an energy system. And I'll come back to this with some other results we have. This is a very big data problem in the sense that you have each node on this graph has a price. And these prices are being set in 1 hour, 15-minute, and 5-minute intervals. And there's about 8,000 nodes in California. So this means that you have over 1 trillion prices in the California system for 1 year. So I think this qualifies as big data. And if you download this and you don't compress it, it's 0.5 terabyte. So that's not trivial to work with. But I'm going to show how we can use optimization physical modeling to encode a lot of, or decode a lot of interesting signals from this. I never get PowerPoint to behave, but there is an animation that I'm not going to show where these move in sync, and you watch a whole week unfold in 30 seconds. And what you'll see, if I got that to work, was that you have a lot of volatility at these fast time scales. You have localized volatility at the slower time scales, and you kind of have these spike shocks in the system in the real-time market. Okay. So imagine you want to put a battery somewhere. Where should you put it? And how can you take advantage of this volatility doing energy arbitrage? That's the question we want to ask. Okay. Now it's a little bit even more complicated. So far I've been telling you about these energy markets. So we have the day-ahead market with hour increments and the 15-minute and the 5-minute real-time dispatch. There's also these ancillary services, and this is what keeps the grid running. So at the fastest time scale, we have this power or frequency regulation. And if you agree to do this, the grid will send you a power set point that you need to track every 4 to 10 seconds. So you need a lot of dynamic flexibility to handle that. We also have these spinning reserves and non-spinning reserves, and they provide additional contingency. So the idea is, if I somehow had control of all of Notre Dame's power and I flipped the switch, right, there would be a big spike in the grid. And then kind of generators near us, they would change their set point within less than 30 seconds to accommodate for that. And maybe if Notre Dame's power consumption was big enough, it might have to dispatch some reserves. Okay. So this is complicated. And if you're a generator, you need to solve the optimal market participation problem. So here's a little table that shows the different kind of time scales and the different products that you can buy or sell energy, or you can offer this ancillary service capacity, and the grid won't let you allocate more than 100% of your capacity. There's no double dipping. Okay, so you want to be able to form a schedule. So here's a result. I'll show you how I got this in a little bit. And this particular result, so the purple is when you're selling energy. So this generator goes from selling to spinning mode, selling to spinning mode. And then the blue and the red are this regulation capacity. So this can be very non-trivial. All right. So how do we figure this out? Turned out that this multi-market problem no one had really studied holistically. So we put together an optimization modeling framework. So I went through all the market rules, which were written by many lawyers. They were not, and then translated those into mathematical equations. Okay. So, and we were careful how we set up this discretization. So California has these 3 time scales and then a day, but the model behind this is set up so you can have arbitrary arbitrary time levels. So you could model like the PJM or the MISO market. And they also set this up so that the physics of the system is abstracted away from the market rules. So this allows us to plug in different energy system physics. If you came to me and said, oh, I think I have this new crazy idea, here's a model for the physics of the system, we could very quickly estimate its potential. All right. So there's a huge number of decisions in participating in the market. So if you look at a 1-year optimization problem, you want to estimate an annual revenue. This is going to be 300,000 variables. But we can solve these with state-of-the-art optimization methods. Right. So to give a little bit more insight, here's the same idea, but in equations. And really, what this boils down to, if you go through the rules, is there's bounds on like double counting. There's restrictions on how fast you can ramp systems. You calculate how you calculate revenue. So this gives some idea behind this model. And what's nice about this abstraction is the interface between this system and this model really is just in the net energy. So how much you're changing. So put together a software framework to automate this analysis. So there's some Python code that goes in downloads in a rather convoluted way all of the data. And then that gets added in to a resource model. So we have this kind of template or abstraction for modeling different energy systems. Those get combined together into the market optimization model, and all this modeling is done in the Julia language. So this is nice. It allows us to model with equations. It's not like you're putting everything into a matrix or something. It's very natural for engineers. All right, and then this all gets aggregated together into an optimization problem, and you can solve this with Gurobi, Cplex, IPOpt if it's a nonlinear problem. There's interfaces to solvers that do deterministic global optimization, and then we have some visualization code. So I want to talk to you now about, demonstrate this on a very relevant issue. So California has decided that by 2020, or I think they might have pushed this date back a little bit, they're going to install 1.3 gigawatts of battery capacity in their state. And for reference, their peak load is about 40 gigawatts. So this is a sizable investment. And here are 3 that have been installed so far. And a very natural question is, does this make sense based on the market revenue, or is this just kind of the state dreaming up something and mandating? And what's really interesting about these systems is if you look at their storage size, their power rating, it's a factor of 4. So all these have been designed or mandated to have 4 hours of storage at maximum discharge. That's a really peculiar choice. We can see if that's the best idea. And these are big systems. So these prices aren't disclosed, but I was able to back of the envelope calculate this Tesla system at $45 million. So took this framework, put together a pretty simple model for a Tesla power pack. It has an energy balance in it. There's a round trip efficiency. And then could ask the question of what's the best way to participate in the market over a year. And this is constrained by the market rules and the physics for the battery. Okay. And we can do a parameter study by looking at different ways to participate in the market, different locations in California, and different storage sizes. Okay. So that's what we did. And, too far. So here's a very interesting plot. So what this plot shows is a bunch of different ways to participate in the market. So blue, so this 1, 0, 0, that says day ahead, neither the real-time layers, energy and ancillary services, or just energy. So this line right here shows you, as we change the storage size in hours, how the payback period changes. And notice it goes from like 120 years to 60 years to back up. All right. So this is the way that most economists or engineers that work with economists analyze energy systems. They only look at the day-ahead market and energy only. And based on that analysis, this is a very bad investment. 60 years is not a good idea. But if you look at participating in some of these faster market modes, or all of them simultaneously, you can get this payback period down to about a year or two. And that is actually really interesting. So the state has set a policy that actually the economics make sense if you strategically bid into the market. Okay. But the other interesting thing is see how this bottoms out at about 2 hours of storage. These systems bottom out at like 15 minutes of storage. So this 4 hours is vastly oversized. And the reason is most of this comes from fast fluctuations in the real-time market. Most of the money is not bought from buying in the middle of the day and selling at night. Could go a step further and look at where do you actually want to locate in the state. So we have data for every node, right, for all these market layers. So this plot shows all the nodes that we have GPS locations for, and each node you resolve this optimization problem. And it actually only takes that year-long optimization 10 to 30 seconds to run, and each node is independent. So although this graph took 200 CPU hours, if you generate it in serial, you can generate it in a matter of hours using a resource like the CRC. Okay. And what we find is really interesting. So the systems that have been installed so far are around here, but the best place to locate is in the middle of the state, like near Fresno. So something I'm very curious about and I don't know the answer to is if I was the grid operator, where would the best place to install these batteries be? And if it's not in the center of the state, there's a problem. Your market incentives aren't aligning with what you want to accomplish, and perhaps your market mechanism needs a little bit of modification. Okay. All right, so that's a very interesting kind of public policy economics question. We can also ask a much more interesting technical question. Right? So we're going to switch technologies to sodium sulfur batteries. So these have a lower round trip efficiency, about 70%, and they also can do about 4,000 cycles to failure based on what was state-of-the-art in literature a few years ago. Okay, and here's some costs from literature for a 1 megawatt hour system. So now we're going to change our framework and add this degradation into the model. So we're going to say every time you charge and discharge, you lose some fixed capacity, and see how this changes the results. And we'll add storage size as an optimization variable. So this is a variant. Now, here, because you have degradation, you have to actually define a time horizon for how long you're going to replace the battery. So here's some results. So this results in a linear program. 5 million to 7 million variables and constraints, but you can solve this in 2 hours or less on average on a single core on a not terribly expensive computer. All right. So what results do we see? So these are fairly interesting. So this plot takes a little bit to explain. So the gray here is if I had no degradation. That's my ideal case. Blue is this kind of medium where we're currently at with technology. And then we can look at an order of magnitude perturbation in both directions. So this low red case is like someone invents battery materials that are 10 times lower degradation. Maybe they deserve a Nobel Prize for that. That's probably a huge breakthrough. What does that mean for the economics? Okay, so those are the colors. These represent the day-ahead real-time market or both markets. And then these two groupings are energy only, energy and ancillary services, and that pattern repeats. Okay, so what do we see from this graph? Well, doing energy only is a bad idea. You lose money. So scrap that in the day-ahead market. If you add these ancillary services, do reasonably well. But what really is interesting is if you add, there's a synergy between ancillary services and also participating in the real-time market, where you see this 4x increase in revenue. So that's really interesting. That wasn't expected. The other thing is that this order of magnitude perturbation in material properties, or this magic material that has absolutely no degradation, that's only about a 10% impact on the revenue of this thing. What's really most important is how you bid into the market. So this is interesting. This is an idea of how kind of the systems analysis can help inform kind of materials side research. All right. And this 4 times increase, this corresponds to a 2 to 3 times increase in the optimal size of the battery. But I want to note that even for this technology, the optimal size is less than an hour. And again, remember, California was installing those 4-hour batteries. Okay. Then we can also look at, well, what happens if I change the replacement strategy? So I replace every year, I replace every 2 years, replace up to 15. It doesn't really make sense to go beyond 20 because other things start to fail. And what you see is, so first you can calculate a maximum possible revenue. So this is if you have no capital cost and you have no degradation. But what we can see is there's so many degrees of freedom in how you interact with the market that you can strategically change how you operate in the market to really mitigate the impact of degradation. So you could, in principle, have one of these batteries operate 20 years as long as you had a really good market bidding strategy. Okay. So, time. All right. So I want to change a little bit and talk about some other things with looking at similar ideas but with concentrated solar power technologies that have energy storage. Okay. And this gets into the dynamic mixed integer optimization. Right. So there's 2 broad classes of these technologies. There's the power tower system. So you have this field of heliostats. So these mirrors, they concentrate sunlight onto the central receiver. You heat up a fluid. You can then run a thermodynamic cycle. So all the mechanical engineers in the room should get excited. Right. So these systems are pretty big. So this is the largest one in the world. Cost about $2 billion. Only powers about 100,000 homes. And this is 14 square kilometers. So in reference, Notre Dame is 5 square kilometers. So like 3 Notre Dame campuses just filled with mirrors. That's the size scale for this thing. I've been told you can see this from an airplane. All right. Here's a little bit more modest of a system, a parabolic trough system. So the idea here is you're concentrating sunlight on this tube, and you have a heat transfer fluid like a molten salt or just an organic thermal fluid flowing through. And again, you run a power. You run like a Rankine cycle. So both of these systems are real systems, fairly recently built. They both don't have storage, and this is how these systems are financed off of kind of this constant or this like levelized cost of electricity guarantee, where you have like a guaranteed rate for 20 or 25 years. But if you look at the data for California, for example, there's definitely a case for storage. So what these graphs show is broken up by quarter, energy price in blue, and the dashed red line is solar irradiance. So what we see is they're out of phase. So there's so much solar in California that you get your lowest prices in the middle of the day, and then right when the sun sets, you get the price spike. So naturally you think there is a case for a little bit of storage. But what would that look like if you're concerned about how you actually operate the system and how you would bid into the market? So we're interested in what's the optimal way of scheduling, so deciding when this should be on and off, and how to control the system in terms of how to manage the mass and energy flows. So this is a kind of a schematic for one of these parabolic trough systems. You see that we have 2 storage tanks. There's a Rankine cycle. There's a bunch of heat exchangers. All right. So the decision variables are how you bid into the market, how mass and energy flows in the system. Your input data are your market prices, your weather, and how big the solar field is relative to the Rankine cycle. So need to augment to our market rules some notion of having different modes, right? So the batteries you can turn off and on with little consequence. Power plants, you cannot do that. So here we're modeling power plant being on in generating mode, being spinning mode, being in non-spinning mode. And depending on these modes, you can participate in the market different ways. So if you're generating, you can sell all the ancillary services, you can buy and sell energy. But if you're in spinning mode, you cannot sell regulation. You can only sell spinning or non-spinning reserves. And if you're in non-spinning mode, you can only sell non-spinning reserves. So this kind of hierarchy is encoded into these algebraic constraints, where these are integer variables. So restricting this, and then also a double counting constraint. On top of this, you can add additional constraints about how long, if you transition from off to generating, that transition takes 3 hours. Or other information can also be augmented to this model. So here we set up a dynamic mixed integer optimization problem where we want to maximize revenue. U are our controls, that's how we bid into the market. And what's very important is these market rules and startup and shutdown limits taken that we developed or taken from literature. These can be expressed as linear inequality or equality constraints that are linear in the discrete decisions. Then we have our CSP dynamics, which we model as differential algebraic equations. These are unfortunately non-convex. And then we have bounds on our differential states, our algebraic states, and our control variables. All right, so if you want to plan for one day, this is a moderately sized problem with 8,000 continuous variables, about 70 binary variables, and about 10,000 linear and nonlinear constraints. But this is a fairly difficult problem to solve, and I'll actually show how a lot of out-of-the-box mixed integer and nonlinear programming solvers cannot solve this beyond a few days. Okay. So to get around this, came up with a decomposition algorithm, and this exploits the model structure. So first we set up a scheduling problem. Which this can be formulated as a mixed integer linear program, where we have this linear surrogate model for the dynamics. I'll come back to that in a minute. Can then solve this to get an optimal operating schedule. So this is when you're going to have your on, your off, your spinning mode transitions. And then you can set up a problem where solve this with the integer decisions fixed. So now this is a standard nonlinear optimization problem. So both of these problems can be solved with off-the-shelf solvers. We use Gurobi and IPOpt. Then from this, you get a detailed state information. So this is temperature and energy flows. And that can be used to update this surrogate model. And kind of the magic that makes this work is here the states that we're tracking are the mass and temperature holdups in the tank. Right? But here, we track the mass and energy holdups, and this allows us to write linear mass balances and linear energy balances. And we notice that mass, temperature, and energy are just coupled by the heat capacity of the fluid. And we can kind of relax this coupling with bounds, and we apply this delta T parameter that's like a trust region parameter. So we kind of relax this coupling, but we constrain using the detailed profile calculated here so it doesn't get too far out of whack. Okay. So this is kind of the physical intuition behind this algorithm. We haven't been able to prove that it converges, but we have some very nice computational results. And this actually makes sense if you think about it, right? So that temperature evolution in a big tank isn't that fast. So you can linearize around it. All right. So here are some computational results. So here, red is the discrete the scheduling problem. Blue is the nonlinear optimization problem. We see after about 5 or 10 iterations, this converges. We also have some benchmarks against off-the-shelf MINLP solvers, different algorithms implemented in Bondman. So this is an open source MINLP solver. The takeaway is we can get the same results as Bondman, or within 3% of the best value found, but 3 to 100 times faster. All right. What you get out of this optimization are schedules that look like this. So this was actually from previously a result. So what this is saying is for one of these CSP systems, you make money by being on when energy price is high, and then going into spinning mode when it's low. So With the spinning mode, you pay a small energy penalty, but you still get to monetize that hardware that would otherwise be off because of your limited energy storage. Okay. This graph just reminds you that we are tracking detailed states like energy holdups and power coming in and power leaving the system. Okay. And then finally, we can do comparisons to look at different markets, energy only, energy and regulation, energy and spinning reserves, and full market participation, and looking at how this changes. The really interesting thing is if you go from looking at energy only participation to adding these ancillary services, you can get 50% more revenue. So what this means is very small modification of how you operate things. You're not buying any extra hardware, but you can have a huge increase in the bottom line for these systems. Okay. So kind of the takeaway is we're combining physical models and data in optimization. And the optimization is capturing what's the best way to interact with the market. And then we can go from this data set with 1 trillion prices and actually make a lot of sense about it. And we can look at what happens if we change physically meaningful parameters like degradation rates or round-trip efficiencies or other types of efficiencies. So batteries actually turn out to be a reasonable investment, payback of 1 to 2 years. It seems like near Fresno is the place to be based on 2015 data. That's very interesting. And with these solar thermal systems, like I said, you can get 50% higher revenues with these ancillary services. And you can actually come up with some nice decomposition algorithms for these types of systems where you have thermal energy storage that actually make this mixed energy or dynamic optimization problem tractable. Okay. So if you're paying attention, you probably have one beef with this analysis. This all assumes perfect information in the sense that you can perfectly forecast prices. Right? This is clearly not reality. There are some nice papers that show for just the day-ahead market with very naive forecasting, you can get 90% of the potential revenue or the perfect information revenue. So that's not, so there is some usefulness about this. So we're calculating our upper bounds for revenue. Not sure how this extends to the multi-scale case. And what this really boils down to is how do you model uncertainty in this multi-scale spatial temporal variations. So this is something that one of my new PhD students is looking at. If you have any ideas, or if you're kind of in the data science camp, and this is interesting, and we should talk, because this is a very fun data set. Good real problem. But I did want to take the last 10 minutes to talk about stochastic optimization on perhaps a more defined problem. All right, so this is a very classic problem from controls literature. How do you optimally tune like a PID controller? How do you select the gains to be very robust? So this is a feedback controller. And we're going to view this from the lens of stochastic optimization. All right, so here's our dynamic optimization problem. We want to minimize some cost function subject to our dynamics, our control law. We could have constraints on like path constraints on bounds or safety constraints. Subject to our initial conditions, our decision variable is going to be our gains. And our problem data, which we'll just think of as random, I'll get to that in a minute, is going to include our initial conditions, our state trajectories, our disturbances, and our model parameters. So I'm going to now take this problem and always represent it in compact form, where we want to minimize this compact objective that's subject to the decision variables and the input data. And I'm going to represent this feasibility set so all these constraints collapse down as such. So like I said, this is a very well-studied problem, but we're going to take a new look at it where we're going to say, view this as a stochastic problem. So Mihai, who was here last week, talked about optimization under uncertainty. Some people call this stochastic optimization. I'm going to use these words interchangeably. But what we want in this context is we want to minimize some expected value of our cost function and make sure that our feasible set, our problem's always feasible for any realization of this data. So we're going to model that data from the previous slide is this random variable with an associated density. And this, again, it has to be feasible for all possible realizations. Okay. So this is an infinite dimensional problem. if unless you have a special class of problems, you can't solve the infinite dimensional version. So a very common thing is to have some type of discrete approximation shown here, where you have realizations or scenarios. There's a weight associated with these scenarios, and we just enforce that these constraints are all feasible for this over this discrete set of scenarios. Okay. This is very common. Mihai talked about this last week. So I just want to give some ideas of some machinery that's available in the stochastic programming community. So one idea is the sample average approximation, and with this you can do statistical inference. So the idea is that you want to calculate, you're going to generate these realizations, and you want to calculate bounds on the objective and on the solutions. So for the upper bound, what you can do is generate T data batches. Each batch has n bar IID realizations. For each batch, you can then evaluate your cost function for just realizations of your random data. So you're saying, all right, given this, these controller gains, how does this perform over these batches of randomly generated input data? And then with this, you can construct a confidence interval. This is a confidence interval for the upper bound. You can do something similar with the lower bound, where you're going to generate different data batches, and then for each batch, you're going to optimize the controller and get an optimal gain for that specific batch. And then from that, you can construct, again, these bounds with this confidence interval. So what does this look like? So here's some simulations where we did this, looking at, as the number of scenarios increases, how the bounds for the objective change. So blue is the lower bound, red is the upper bound. These are randomly generated batches, so they can cross each other. And then you can see that, as the number of scenarios gets down, kind of the bar here shrinks. Likewise, you can look at kind of the variance in one of our decision variables, the integral gain. Okay. So this is a really powerful technique and a nice framework to say, when is good enough? When do I have enough data to be fairly confident in this discrete approximation to my solution? So that's one idea from stochastic programming. Another is this idea of risk metric. So expected value is not always the best idea. Sometimes you want to care about other points in the outcome. And conditional value at risk, this is a coherent risk metric. And what it is it's the expectation over the 1 minus alpha probability tail of bad outcomes. So this is parameterized in alpha. And so it generalizes average to worst case. And this is very nice because this is you can reformulate this to be convex into optimization. So what this graph here on the left shows is tuning one of these controllers using CVAR as our objective, and then comparing this with another alternative. And what we can see was, because we're using CVAR and we're focusing on this extreme tail, this kind of gets shifted over. You get a little bit higher mean, but you can shift these extreme outcomes over. So this is another nice feature to know about, or existing machinery in stochastic programming. Another are sparse grids, which are great for the worst case scenario. So the idea with a sparse grid is you have a quadrature rule, kind of do a sparse tensor product, and you can get these very nice structured sampling techniques. So here's a sparse grid with about 400 samples and 1,000 samples compared to just vanilla Monte Carlo sampling. All right. And what you can see is these are much more efficient, at least for the worst case. So here's some computational results. And we see that with about 70 realizations, we start to get convergence in the worst case and convergence in our optimal parameters. But even after 1,000 samples with Monte Carlo, these quite haven't converged, and this has not converged yet. So if you have structure in your uncertainty, so here uncertainty each dimension needs to be independent, or needs to be such that you can transform it to be independent, sparse grids are very computationally efficient. Okay. Final thing I wanted to note on stochastic programming is there are some very nice scalable algorithms. So kind of here's a standard form for the problem where I'm going to combine every realization, and then there's some type of constraints that link the realization. So we say, all right, I'm going to tune this controller Those gains need to be consistent across all of the realizations or all the scenarios. Well, I can write this in a lifted form where we introduce these lifted variables for each scenario and then this simple coupling constraint. Based on this, you can take the first order optimality conditions or the key conditions, write them in this block bordered diagonal form, and then this is decomposable using a Schur complement. This was discussed the previous week. We actually used software from Argonne Pips NLP to run this comparison. So this is optimal PID tuning for a distillation column. So I am a chemical engineer. And what we can see is great scale up as we go from one node all the way up to 24 cores. So kind of to wrap this up, my background is in this optimization in stochastic programming. I think there's a lot of great things from stochastic programming that have to offer our community here. So this is a way to explicitly incorporate decision-making under uncertainty. Very nice framework to do this. There's a lot of great theory. Can calculate or capture risk aversion with coherent risk metrics such as CVAR. These types of models and the other work I've been presenting, they're algebraic or they're differential models that are then converted to algebraic equations. Those tend to have a lot of sparsity, and that can be exploited for very fast linear algebra. And we also use exact derivatives. So this is why we can have problems that have millions of variables and constraints that solve quickly. Furthermore, these stochastic programming algorithms can exploit the problem structure in the sense that they tend to be few orders of magnitude fewer variables that couple realizations than variables that respond to uncertainty. There's nice theory around approximations, so sparse grids, sample average approximation. But a key downside to stochastic programming is you need the probability space to optimize over. And most people in this community just say, step one, assume we have this, or assume a special form of this, and here's some great result. So I think uncertainty quantification, especially for aspects of the center here, there's a great marriage with stochastic programming. These provides framework to actually determine what are the appropriate probability spaces from data. So this could be weather. How do you model weather to have these forecasts? And I'm really interested in model simplifications. So if you have some physical model that you simplify, how do you capture that and how do you actually embed that into an optimization problem? So I'm a little familiar with the work of Kennedy and O'Hagan, but I know there's other people that have worked on this. Okay, so Ed, there's a couple other collaborators in here. So I'm interested in getting down to the material scale. So here's two projects that we're currently starting. And the idea is, one is nanoengineering of membranes, the other one's molecular design with Ed and a few others for thermoresponsive solvents for solar desalination. How do you kind of couple this material scale, whether it be simulations, whether it be actually synthesizing something and measuring thermodynamic properties with kind of this system scale optimization and loop around. So a couple things that are really interesting. How do we take kind of laboratory scale uncertainty and propagate that through these types of design problems that are cast as optimization problems? And then how can we go back and systematically design experiments? Okay. And then finally, I have some self-promotion. So I'm going to be teaching a graduate elective in the fall of 2018 on nonlinear and stochastic optimization. Hopefully this will be set up in a few weeks. And then we're also going to host a Pyomo Fest at Notre Dame. So I mentioned Julia. Pyomo is another modeling language. So Pyomo is this open source package to model optimization problems kind of in, it's very natural for engineering kind of in just as algebraic equations or as differential algebraic equations. Then this interfaces to all the solvers that are available. This interfaces to automatic differentiation that calculates Hessians and gradients. Okay? So Pyomo is out of Sandia National Lab. We're going to have 5+ developers from Sandia. So these are people that actively contribute to Pyomo, but they're also domain experts. So they have a background in like power flow, inverse problems, public health, energy systems. The list goes on. So the hope is a lot of graduate students and postdocs from this community and other communities across campus will be able to come, maybe have some optimization problems in mind within these 3 days, learn about this tool set, and perhaps prototype code for their research problems. And special thanks to Yark and CRC, who's helping sponsor and doing a lot of the logistics for this. All right. So in conclusion, is Alex Dowling, new professor in CBE, very interested in mathematical optimization applied to energy and water problems. Happy to take questions.
Any questions?
For the battery optimization of the economics, so you said if there was no degradation, you compare no degradation and then 40,000 cycles, 4,400. So can you shed some light on how, when a battery can last 10 times longer, full cycling, that the revenue can be so minimal between them?
Yeah, so I like to think of it as if the battery was much worse. Why isn't the revenue so much worse?
Okay, yeah.
And the reason is there's a lot of opportunities in the market where you would perhaps have half the amount of cycling, but you'd still be able to make 90% of the money.
Okay.
And it's the fact that there's very sharp diminishing returns.
Okay.
But that's a fascinating.
So keeping it charged maybe 80 or 90% most of the time, so that the battery can last 20 years or something.
Yeah,
That's
yeah.
Kind of
Right, or you find ways that have less cycling.
okay.
That maybe you get 90% of the money, but there's so much less cycling.
Right. Okay.
Any other questions?
You were doing the locations of where these storage should be. Fresno was the magic place. I mean, obviously I don't know all the details that went into the model, but what's the kind of key factors that determine location? Is there distribution costs or?
Yeah, so we're looking at historic prices for 1 year. So something was happening in Central California that was causing a lot of volatility, such that you want to put a battery there.
Where it's the most volatile.
Right, right. Now, there's a really interesting question that stems from this is what was physically happening there? Do they need to put in a transmission line, or was there a big wind farm there that was adding all these stochastics? And because we're not modeling the grid, we're using the results from the grid as input data. We don't have those insights. But it tells someone who is, from the California grid, something strange is happening here. You should look at this.
I have a question
Yeah.
on the stochastic optimization and the parallelism. Some of the systems that we are dealing with are very, very large.
Yeah.
Do we have some stochastic optimization packages that run on 2.5 million cores, not just 25 cores? How because you talked about high performance
Yeah.
computing and scalability, I would 25 cores, you are still in most of the cases on one node
Mm-hmm.
in modern heterogeneous
Yeah.
architectures. Are there some packages like that would do that at that very large scale?
The answer is yes. I don't have experience with them, but I know at least 2 or 3 of the folks from Sandia that are coming do this.
Yeah, we work a lot with people at Sandia,
Okay.
Lawrence, Livermore, and Los Alamos. Have some experience with some other packages that they are working, but it's an open issue. It's a big problem.
The key thing with the parallelism here is if you have you want a few orders of magnitude fewer of variables that are coupling or kind of across all of the scenarios compared to variables that are inside the scenarios. So for the controller tuning, this actually works out fairly well because there's not a lot of design parameters, but there's a lot of variables involved with the dynamics of the response. If you had a problem where it was almost all design variables, you can't do that much.
In stochastic optimization in general, the selection of the realizations is critically important. Okay. let's forget worst case design, let's say ultimately let's say min-max problem, very, very tough.
Yeah.
But an expectational, optimization or risk optimization and how you will select the realizations is very important. Any, are you thinking of any adaptive ways as your algorithm sort of moves in the design space to update those realizations, or you just marry them sort of like an exterior sampling and you just use them for your whole optimization?
Yeah, so I think kind of the vanilla thing to do is to not do something adaptive. I have thought a little bit about that. I unfortunately missed your seminar earlier in the week because my students went and reported back. I know that you were talking about that. We should get lunch sometime.
Well,
Steve?
yeah, one quick one. So back to the thinking about Fresno, you said that there's a lot of opportunity there because there's a lot of volatility. But at the same time, this prediction supposes perfect information, and I would imagine that higher volatility would adversely affect your ability to predict what's going to happen. What is a realistic kind of resolution between those two competing factors look like, do you think?
I think it's a very open question. People have shown with like the day ahead stuff, it's pretty predictable, which is why the perfect information assumption isn't that bad. I don't know how that's going to hold.
Well, with that, thanks Alex for that.